So yeah, the topic for today is signal processing and machine learning inference on the edge. Quite a hip topic, very, very interesting and relevant. From Kai Wolf. You might have heard of Kai Wolf already. A couple of months ago, I don't know when it was, January maybe, you held a talk in the C++ user group Frankfurt, where Karlsruhe joined in. So I guess a couple of Karlsruhe meetup members will know you already. Okay, Kai, the stage is yours.
Okay, thank you. All right. Yeah, as David introduced me, my name is Kai Wolf. I'm working as a software, so I'm a computer scientist by day. Doing this for quite a few years now. And right now, or for the last few years, I'm working as an independent software consultant / senior software developer / software architect. Mainly, but not exclusively, in the following areas. So I'm doing a lot of computer vision or image processing based projects. Usually, they also require some type of machine learning or deep learning, but not always. Besides that, I'm doing mobile computing, but here mainly Android development, as well as embedded development. And yeah, also recently I got more into the software architecture side of things, as well as build systems and DevOps. So yeah, this includes just the whole software lifecycle, and also for a few years now, actually, I'm doing I'm getting into projects where there is some performance optimizations required. So this can be like either specific processing algorithm on an embedded platform, which needs to be as fast as possible, or at least receive, say, 30 frames per second, or audio processing, which is also be a part of this talk today. So my clients do come from a wide range of sectors, such as automotive. I mean, I'm located near Frankfurt, so this obviously makes sense. Generally, technology provider of any sorts, like hardware companies, medicine stuff. I also do work, or like to do work, for startups, because this type of work usually focuses on different aspects than, say, a Fortune 500 company. So this just keeps me interested in several topics, as mentioned above. So the outline of this talk will be, as I said before, I will be talking a bit of digital audio processing. So I will introduce a few basics which are needed for getting to, or to grasp the topics I'm going to cover today. Also, some usual constraints and requirements for real-time data processing. So for your camera data, for your audio device, and also different hardware requirements. So if you're targeting an embedded platform, or say ARM chip, which is much more popular now thanks to Raspberry Pis and Apple macOS, you usually have different approaches depending on your target hardware architecture. And then finally, I will introduce to the now deprecated RenderScript as of 2 weeks for now. But still, it's an interesting technology, and it's a perfect starter for getting into the second or main topic, which is Halide of this talk, as the architecture or the approach is in some aspects quite similar. So if we talk about audio processing, I have to say that I'm not an audio processing expert, so my knowledge is also limited. But if we, for the topic we are going to cover today, we can look at audio processing as that there are sound waves which hit the membrane of your microphone, or your recording device, or your ear in that matter. And then it gets converted through an ADC, so analog digital converter, into your sound card. And from there, the sound card pushes or puts the data, or the sound driver on your sound card puts the data into your OS. So this is usually for sound, for most modern PC sound devices, it's like a push processing, and from the so it lands inside your kernel from your operating system, and from there it gets it's traveled through your audio API, which also depends on your operating system, but can be either like Core Audio, Jack for Linux, OpenSLAS for Android, etc. And from there, you have access to the incoming audio data through your audio application. So, and from there it gets back, like, again, through your audio API, through the operating system, and then through your sound output device. And if we look at the raw data, I mean, there are many different formats, or not that many, but there are quite a few formats in which the incoming audio data may be formatted. Can be either be 16-bit integer, for instance, but most commonly, or almost all APIs, at least as I'm aware of, do support floating point data, which is what we're going to look at right now. So the incoming audio data, it's normalized between -1 and 1, and it has to be sampled in some way. So again, we're talking, so sound waves is like an continuous analog signal, which needs to be sampled, and the sample rate is usually 44.1 kilohertz, 48 kilohertz, or 96 kilohertz. And the reasoning behind it is that if we look at the human ear, then we humans, we can hear sound or noise between 2 hertz and 20 kilohertz. And according to the Nyquist theorem, we need at least twice as much. The sampling rate has to be at least twice as high as what we going to sample. So at least 40 kilohertz are needed, so that we can hear the whole range of audio. And so 44.1 kilohertz is looks actually quite funny number, but the reasoning behind it is it has some nice properties. For instance, 44,100 is the product of the first few 4 prime numbers, so the square of the first 4 prime numbers, and with this it has some nice numerical properties. So it's evenly divisible for many different sizes and so on, and usually sufficient for now. So, and if we want to do some operations on this audio data, we have an audio buffer, and also I forgot to mention, this is mono data, but there can be two audio samples, or 2 channels in that matter, which is stereo, at least, or for some digital systems, there's like 2 channels, 5 channels even, for Dolby Surround maybe. And but in this case, we're looking at 2 channels, and this audio samples, so this sample audio data comes pre-buffered. So a few audio samples are gathered before they get pushed through your audio application. And this buffer size usually depends between 32 and 1024 samples. And again, if we look at the audio application, which gets fed with the digital audio data, then we have some kind of callback for push-based processing, which may look like this. So on Android, it looks like this if you happen to use Oboe or OpenSLAS. So you have like your void pointer audio data, because it can be like I said before, floating point data, or 16-bit integer, for example. And you have a number of channels and a number of samples. And you need to take care that everything, every work we do inside this callback adds to the overall latency of the audio. So if we think, or if you look at this, so we have incoming data, incoming audio data, and it gets gets processed in your application and then put out. And the longer you work on the data you currently have, the more latency you will introduce to the whole system. So, in fact, it looks as schemed here. So you have your audio buffer, which is filled with incoming data, and you do some processing on it, and then you get the next audio buffer and the next audio buffer and the next audio buffer. And if it so happens that you need to do more work, so the work you're doing with your audio data takes longer than the time the audio buffer needs to fill up with samples, then you have some glitches because you can't process them in real time anymore, and you introduce glitching or draw-offs. So, and if we look at the latency here, the round trip latency, so from the input microphone to the output speakers, it depends on the task at hand, but it's usually fine up to 10-20 milliseconds. It very much depends on the sound. So, for instance, I'm a guitar player. If I'm recording my instrument, then anything above 10 milliseconds is already noticeable and not good anymore. So, for recording instruments, so for very snappy sounds, it has to be below 10 milliseconds because we can actually hear this latency. And for language or interactive talking, it's up to 30 milliseconds is usually just fine. And again, the latency introduced to the system also depends on the buffer size. So I've just put into a table here the buffer length, or the actual length of filling up the buffer for the 44.1 kilohertz and 96 kilohertz sampling rate. So if we have, say, 64 samples, and we have a sampling rate of 44.1 kilohertz, then it already takes 1.45 milliseconds just to gather the data without doing any processing at all. And for 96 kilohertz, it's a bit faster because the sampling is much faster, or twice as fast. It's 0.66 milliseconds. And you can see already that if we need to work upon or do some work on 1024 samples, it's already so much. So the buffer is so large that it's usually not suitable anymore for like real-time recording instruments and stuff, because it's already the latency is already noticeable. So, and besides filling up the buffer, so we are going to look at Android right now because this is what I'm most familiar with. The hardware itself also adds some additional latency to the table. So we have this ADC converter, as I already talked about, and then from the sound chip, it gets actually physically transferred over onto a bus to the audio driver audio sound card inside your mobile phone. And then you have this audio flinger and it is on Android. It's called audio flinger, which is an own thread which does pre-buffering of the incoming audio data and also does some conversion. So if you want your application to receive floating point, but the sound driver only supports, say, audio driver only supports, say, 16-bit integer, then it needs to do the conversion, which is happening here. Then you have this binder, which is the shared memory on Android. It's a shared memory for IPC, for inter-process communication, which talks to the rest of the application. So it's so-called enterprise bus for the different applications. And then you have your audio record thread, which is usually the API we're talking to. So as I said, for Android, it's usually OpenSLES or A audio. And then finally, it gets to your user application ring buffer. So the audio samples usually get stored in a ring buffer because it's more memory efficient. So, and you can do your work here, and then it goes all the way back through the output of your device. And this also adds a lot to the audio path latency. In fact, Android is unfortunately particularly bad at audio processing. And this doesn't include different protocols such as Bluetooth, for instance, where there's additional protocol latency involved. And here I just put down to a table a few measured additional latencies for several devices. I mean, granted, it's like an old Android version. I think we are now at Android version 11 or 12 even. So some work has been done already, but most of or many devices of these devices are still in the wild outside today, and they have like terrible latency. So say this Google Pixel XL or Pixel 2, for instance, does introduce already 18.1 milliseconds of audio latency without doing anything meaningful with the data itself. So, and
what did you mention? Sorry, you mentioned what latency is for music is the maximum before it feels strange. Wasn't that 10 milliseconds?
For recording instruments, yeah. So if you record your instrument and you put in you play, you strum your guitar or you play the piano, which is immediate, and before you hear any echo or before you hear your own playing, if it's longer than 10 milliseconds, so if this delay is longer than 10 milliseconds, you can already hear it. For playback music, so I'm watching a YouTube video on my Android phone or listening to music, the latency is usually just fine because it doesn't matter, right? Because it's there's no real latency because there's no interaction. But if we would talk like if we would talk through the same phone, for instance, and we both would feed our voice into the microphone, then it would be like this latency here. So again, it is for the Pixel XL, this certain milliseconds is fine if we're not doing any much more work which adds to the latency. So in this case, say we have like 6.5 milliseconds before it's noticeable. And so now that we have our audio data and we made sure that we take the fast path and we have it now in our buffer and it's ready to do some work upon it, there's some more stuff which is preliminary for anything meaningful in audio processing. So usually we're not interested in the time domain, so the samples you just saw earlier, but in the frequency domain signal. So we're not interested in the actual waveform, but we're more interested in the. So we do want to do some say we want to implement an equalizer which equalizes certain frequencies, or we want to implement a band filter which tones down specific frequencies or boosts other frequencies a bit louder, or any digital filter in that matter. So we are interested in the actual frequencies, and for this there's like this de facto tool. So we use a DFT, so a Fourier transformation, or FFT, which converts a time domain signal, say the audio wave signal, into a frequency domain representation. Specifically, it transforms the signal from time domain into magnitudes and phases, where the magnitudes, depending on the bin size, represents the different frequency bins and the phases. And calculating the fast Fourier transformation involves the ATAN or arctan2 function, which is in itself a bit costly because we need to look at the different quadrants depending on the phase, if we want to calculate the phase. So, and this is costly due to branching because we need to check if the actual value from the complex number is positive or negative. But that being said, usually this is not a problem because an FFT, so the name already implies it, fast Fourier transformation is almost perfectly parallelizable. So this can be implemented in a fast divide and conquer manner. So this is usually not your bottleneck, but still it's work that has to be done. And also, if we wanted to analyze the different frequencies from our input signal, we have to beware, as I said before, the frequency range depends on the sampling frequency, so it has to be at least twice as much the frequency we're interested in, according to the Nyquist rule. And if we take, like, say, a specific number n of audio samples, which determines our frame size we're currently looking at, then this also determines the frequency bins, because we need to divide the FFT frame size by the Nyquist frequency. And this has in itself a problem. It's also a problem because now we're doing a trade-off between the frequency and the time resolution. So if we take a small FFT, so a small number of audio samples, so we're looking at a small FFT frame, then we can't resolve specific frequencies because they are just too large. So they smear out in the spectrum of some sorts. And if we take longer, so if we increase our FFT frame with more and more audio samples, then frequencies which are very short, or so short snippy signals, they also tend to get lost in the spectrum. So this is usually a trade-off, and it very much depends on the actual application we're going to, or the actual problem we're trying to solve. But we can say that more samples relate to more accurate frequency content and more latency, and also that larger frames relate to less accuracy for temporal events, like snappy short events within that frame. So again, depending on the application, we also have to take this into account. So, but for most real-world applications, as far as I'm aware of, typical values between 512 or 1024 samples are okay, or sometimes even less. So if I wanted to implement an equalizer, I would also even go lower than, say, 256 samples for my FFT frame. And then finally, if we have done our work on the frequency, or have analyzed our frequencies, we do need to take back the inverse signal, so the inverse of the Fourier transformed signal back into our audio stream. And since this is a FER filter, so finite impulse response filter, we need to do some more audio stuff so that it sounds naturally. So this processing includes like overlap adding in time domain. So we are gluing concurrent or neighboring time frames just into another, so that it doesn't introduce any artifacts due to the processing. And now
I have a question for the last slide.
Yeah,
I didn't quite understand the frequency bins. So I would understand that the FFT frame size determines the maximum frequency that can be sampled. But what exactly is a frequency bin, and how does frequency bin relate to the maximum frequency?
So if we take an FFT frame from say 100 audio samples, and then we do the Fourier transformation of it, then we need to interpret the magnitude. So we resolve this 100 samples into linearly sized frequency bins. So we have this continuous audio stream of data, and we take a snapshot of it. So we look at, say, 100 samples or 500 samples, and we resolve all the frequencies which lie inside this 100 or 500 samples. And due to the fact that different frequencies have different wavelengths, right? We can't resolve all frequencies at the same time. So it very much depends on the FFT frame size. So if we have like short signals, or if we have a long signals with a long wavelength, and we take a short FFT frame, it cannot resolve this long frequency, or this large frequency. And vice versa, if we have like a short snappy signal, but we look at a large sample, a large FFT sample frame, then we can't resolve this short frequency, which is just somewhere inside the whole spectrum we're looking at. This is usually, so again, this depends on the signal we are trying to analyze. So it's good to have some understanding of your target signal before. So say if we want to analyze a bongo drum, which has snappy short sounds, I would just look at a small FFT frame, because due to the fact that, again, that the frequency bits are linearly sized in my FFT frame, it would look much better in the spectrum than say for a large FFT frame.
Okay, got it. Thanks.
Okay, so and the last slides just again did cover only the preliminaries and the latency only. So if we wanted to do actual work, say in this talk we are talking a bit about machine learning inference. All the meaningful work actually comes just now, after all this pre-processing stuff and all this hardware latency and all this FFT stuff I just talked about. The actual audio processing happens just now, right? So, and remember that we're still on the edge device, so there's actually a very short time frame that we have available on our hands, that we can do anything meaningful. So, and for this talk, I'm not interested here in the different networks or architectures, but only in the computations for this different machine learning networks. So, in a nutshell, the computational complexity of most neural networks consists of matrix vector multiplication, so the activation weights, say, the convolution of an image or of a 1D audio signal. Then we have pooling, normalization, and also activation. But this is usually very not so costly function. And key operations that need as much hardware support without losing. So these are the key operations that need as much hardware support without losing generality. So these are the operations that need to be very fast, because they do happen the most often in any machine learning inference. So, and for this, there are already some libraries available. So we have CUDA NN from NVIDIA for reference, which mainly focuses on GPU acceleration, but still, so this is the stuff that MKL or CUDA NN is solving for you. So, and if we look at, I would just want to make a short recap to data and computation. So, if we look at fast processing, or if you look at efficient code, then it's hard to reason about any piece of code, because in fact today's computing architecture is extremely complex, and it's not easy to judge from a piece of code by looking at it if it will be like fast or if it won't be fast. So we have on Android, but also on many laptops, we have dynamic frequency control. So the operating system is scaling down and or up the CPU cycles depending on the current load. On ARM, we have big little architecture, so we have several cores which are not powered the same, but some cores are stronger than others and will be used for different tasks. We have multi-level caches, which we will look shortly. We do have vector instructions. So for ARM, we have neon instructions. For x86, we have AVX or SSE vector instructions. We have superscalar and out-of-order execution. So the instructions from the machine code are opt and not processed in a linear fashion, but can be reordered or executed in parallel. So, and also, if you look at the latency numbers from your computer, I think this is a table which probably most of you are familiar of. So these are latency numbers which are typical for typical operations. Say the L1 cache reference just is probably even faster than this number, but it's round about half a nanosecond, and so on. So we want to keep the data right in the CPU and don't want to move data around as much, because this is usually what takes the most time. So if we have the data we need right where it belongs in the CPU, in the registers, or in the L1 or the L2 or L3 cache, then this code ends up being the most fastest. So again, from the memory hierarchy, we have the CPU registers where most of all the computation is happening, and then we have the L1 cache, which is as close as the closest first cache to the CPU, and for most or many architectures we have L2, L3 cache, and then the main memory, which if we want to access data from the main memory, takes the longest from this view. And just to recap shortly, if you're not aware of this, but most probably you are, if you want to do some computations and you have your CPU and you want to fetch some data to do computations on it, then usually, so the red dot is a piece of data you are interested in. What happens is that the CPU is not loading your single data point, but it loads a whole cache line. And this cache line gets transferred into the L cache, L1, L2, L3 cache, depending on the size. So, and if you load another data point from main memory, so RAM, it also ends up being fetched inside the cache line, and this cache line gets cached in your L1, L2, L3 cache. So, and what this means is if you happen to access any data point that is directly neighboring the one you are targeting, it's already there. So there's no need to fetch it from main memory again. So this is a very fast operation. So on accessing the second number, the second floating point value in array, it's already there. So there's almost no time lost. And again, taking the third value from your array, say it's already there. So there's not much additional latency introduced. Is also is true for the second cache line I was just fetching. So, and if we happen to do a write on the cache, so you're writing back, then this whole cache line gets transferred back to main memory, and the cache line gets dissolved from the L1, L2, L3 cache, and it goes away. And this is actually inspired, say, from John Lakos, which gave a CPCon talk quite a few years back. But I found it to be a really interesting and nice, nice concept to keep in mind. So again, we have another data point in cache, and then the whole cache line gets transferred into cache. So, and this leads to a technique which is called tiling. So if we happen to do some processing on data, say an image or audio stuff, then we want to traverse this whole array of data without causing too much redundant access, and also making sure that most of our data is already inside the cache. So, and for this, there are several approaches to tiling. So a naive version would be just to traverse your data in a vertical fashion, which would be very cache unfriendly, as we just saw earlier. And so it would be much better in this case to have like a horizontal traversal. But again, it depends on the size of your actual cache line, so how large your cache size is. And therefore, we have something which is called cache-aware vertical reduction. So we only move on the left side. We only move inside the array up to our cache line size, and then we fetch the next. So this regard, we make sure that we mostly stay inside the cache. And then we also have something which is called SIMD. So it's Neon on Android or ARM, and AVX and SSE on x86. So we have not single instruction, single data, but we have SIMD instructions which do apply a given instruction on multiple data. So we have a single instruction, multiple data, which is also much faster than doing everything, solely or singly for every data point. And with this, I'm going to introduce RenderScript. So RenderScript was C99 dialect language technology, which is still part of Android, and it offers high-performance computation API, and it enables developers to run operations with automatic parallelization across available CPUs. And also, due to to its architectural design, which I will talk about in a minute, it was suitable that you could write your algorithm in RenderScript, and if your device manufacturers, say Samsung or Huawei, did provide support for it on the Android on its Android phone or smartphone, you could be granted that it's like efficiently executed on the device itself. And also, as in Java fashion, you didn't need to recompile your RenderScript code for several architectures on devices, but you could only compile it once, and it would be fed into your APK, and then it would get JIT compiled on the device at runtime. So in fact, it looked like this. You have your Java application. Sorry, I mean your Android application written in Java or Kotlin, which does get generated through the Java compiler into Java bytecode. And you have, besides that, your RenderScript source code, which used the LLM RenderScript C compiler, which also produced LLVM bytecode, and possibly your native code as well. And this all did land in your Android APK. And then the AOSP, so the Android open source project did provide a general RenderScript compiler, which was already able to parallelize your RenderScript algorithm onto different cores on the CPU. But again, if it so happens that your smartphone did have a DSP or a specific GPU, then your hardware vendor could provide a specific driver for it, and this would then get JIT compiled via the BCC compiler directly onto the hardware, which is a nice concept because it solves a bit the heterogeneous hardware architecture which is given on Android. And this was a nice concept and did work. So I did also several commercial projects with it. It did work quite nicely. However, it's unfortunately it's deprecated since Android 12, so since the most recent Android version, because they try to push their ANN network, and also they didn't think that it has like that big of a target audience. So most of the people out there just want to execute or run their machine learning model as fast as possible, and for that there's ANN and TF Lite, which is probably more suitable. But still, it's still widely supported on many or most devices out there, at least as far as I'm aware of, and for all the test devices I do have happen to have around here. And this is already told. So that being said, there's for quite a few years now.
Before we switch to Halide, so this RenderScript focuses on single instruction, multiple data?
Exactly. Yeah. So not exclusively. So you did write your RenderScript code in a C99 dialect, and you could be sure you could ensure that your code is parallelized onto different CPUs. So through the AOSP RS driver, Android open source project RenderScript driver, and for say the Samsung Galaxy phones, smartphones, they also did ship with an so Samsung specific driver, which did end up running on their internal DSP or GPU. Say. So for Samsung, I know that it did run on a Samsung GPU if you enable it. And this was the way it was implemented. So you had like these two parts of your RenderScript code. So one from the AOSP and one from the OEM.
Okay, thanks.
Mm-hmm. And yeah, for quite a few years now, there's Halide, which is more and more catching up or getting more and more known for its performance improvements. So Halide is from a few people. I think it has been fallen out from a master thesis or PhD thesis from a guy called Alex Rankin. He happens to work on it full time. I'm not sure quite about that. But basically, what Halide is, it's a DSL, so it's a domain-specific language in C++, where you can also, as similar as in RenderScript, you formulate your problem or your function you're trying to optimize, and then it gets scheduled. And the key feature from Halide, so the thing which makes it most interesting is that Halide does separate between the formulation of the algorithm itself and from its scheduling, which makes things very interesting. So specifically, there's a separation between what to compute and how to compute it, which makes reasoning about its efficiency very, very interesting. So it helps, to write a high-performance array image processing stuff or tensor kernels. And as I said before, it also targets the problem of heterogeneous computing hardware. So, and how does it work? So you have your Halide header, and then you define your function. In this case, I choose the most simple function ever. So, and also I'm switching now from 1D to 2D because it's visually more pleasing to look at images than to hear audio, and also not so sure if it does work through Jitsi or through my computer. So, but you have your gradient function which just adds the pixel location to one another. So it gives you a gradient image, and this line here, gradient xy equals x plus y. This is your actual algorithm, which is given. This is very, very simple in this case, but it can be anything, right? So it can be any complicated computation you want to do. And then you have your realization step, where you put in your output or input dimension, input and output dimension. And if you execute it, then it just goes in a linear fashion through your image in this case, and it outputs a gradient image. So, and we could now ask, okay, but why am I using something like cuDNN or MKL? Because these are highly optimized libraries, right? And this may be true for, again, depending on your target application. But what cuDNN or MKL or all the other high performant libraries cannot do is they don't have the capabilities to do global program optimization. For instance, you have like different functions you're calling from your high efficient library, and then you always have the synchronization points, right? So you have your you're doing your FFT, so, and then it gets synchronized back to DRAM or RAM for that matter, and then you're doing your machine learning processing, and then it again gets synchronized with the RAM. And these synchronization steps make it impossible to do like a whole global program optimization. Say you want to, we actually know that we do some processing on this data, and like 3, 4, 5, 6, 7 steps down the road, we need this data again on for a specific input from a whole different function. Then Halide is possible to actually, or we, for that matter, actually possible to acknowledge this and see through this and do specific optimizations just for this case. So again, the key design decision from Halide is its separation between algorithm and the Halide scheduling stuff. And what does happen with your algorithm and your scheduling is it gets transformed or compiled into something which is called immediate representation, Halide IR. And this is all powered by LLVM, right? So if you look at the Halide version number, it just equals to the LLVM version because it very much depends or is based upon LLVM. So, and with this intermediate representation, we have all the capabilities that LLM provides. Say we can output specific target for specific target architectures. We can generate specifically Neon code for ARM, say, or CUDA code, or SSE or AVX code, which is really nice. Or also like fixed point operations for hexagon HVX chips. There's also the possibility to emit fixed point operations for it. So next we're going to look a bit more onto examples because I think it makes sense to just look a bit more into it. So if we have if we think of our algorithm formulation, which if you notice we don't have to repeat it, we have written this our algorithm, we have just written down somewhere once, and now we can look at the different schedules for it. So if we want to reorder the traversal from X to Y to Y to X, and it's just like one line, and we can change the traversal order, right? And this gives now
just for understanding. Sorry. So it's not only the visualization which is sequential, but in this case, Halide is also computing it sequentially.
Yeah. So if you would if you would look at the intermediate representation, then you would see that it actually is traversed in memory just like it's visualized here. And again, now that we have our algorithm sorted out, so we don't need to look at this anymore. And just imagine what this would mean if you would write it in C++ or C. Okay, in this case, it wouldn't be that difficult because you would just have to switch your X and Y index variables, right? But say we want to do tiling now, so we introduce two other outer variables, and then we split our image in an X and an outer part, and then also do the reordering so that it traverses in the 4 quadrants from left to right. Then we could already, or we may possibly already can see that it's much more caching friendly, and also we don't need to. So what we could now do, we could now play with these offsets and also this sizes, and just measure the output or the performance of our algorithm without having to deal with the actual code itself. So again, if we would think of the C or C++ code we would have to write, we would have to switch some for loops around, and then we maybe make some mistakes, and we cuddle up our implementation, our actual implementation. So our algorithm would eventually become faulty. So this is not happening here because we're just dealing with the scheduling. And also, I was showing before the simp instructions, so the vector instructions, where we fetch a specific number of data points before doing operations on it. It's also possible here with the split and vectorize, also giving it the size of each vector. And again, it's just approaching or traversing the data in different manners. And it makes it very easy to reason about, and also to play around with the scheduling to find the most optimum version for our given problem, right? Without fiddling with our algorithm. And of course, we can also merge all these different stuff. So we can do fusing, which is changing the index variables around, tiling and parallelization. So this is also being done in just 3 lines of code. And again, try to imagine what it would mean to code this up in C++ without doing any errors again, right? So, and this makes it very handy and easy to do performance optimizations for a given target. And just to tell you a little bit about some of the work I'm doing. So this actually involves quite a lot of stuff I would have to do normally by hand when doing performance optimization work for a given client. So say I have this client and he wants me he has this 3D camera and he wants me to put out like 30 FPS, 30 frames per second for a given image, but it's too slow right now. And this would involve all the things I'm doing. So I would play with different vector intrinsics. I would play with different tiling optimizations. I would do loop unrolling. I would do caching. I would play with different caching strategies. And this is usually something I would have to do by hand, by just coding all the stuff around with much more lines of code than actually represented here. So Halide makes it very easy to investigate different approaches quickly and fast. And if you do so happen to be not as intricate for this kind of work, so you say, okay, this is fine. I mean, right? I could play with it, but I'm not experienced. I do not know what I do have to do here, or how to fill up my cache. This is also fine, because since Halide version 11, so for the last version, there's Halide ships with a so-called thing which is called autoscheduler. So and this autoscheduler does schedule, or does create a somewhat optimal schedule for your problem without having to do anything of this stuff here. And the most recent, or the most popular one, is the Adams autoscheduler. And just maybe to recap, if you think of this, so apparently there is an optimal version here, right? So depending on my target, there must be some optimal algorithm depending on like tiling size, cache size, number of threads, what have you, to get the optimum version. And if you think of it, then it may become apparent that this is just a search tree, right? So you have all these different options, and this is basically a tree traversal where you find the optimum solution. And this is exactly what this Adams autoscheduler is doing. So it's a deep learning based autoscheduler, but it determines the optimal solution for your given algorithm on a given target architecture. And in fact, it produces results that are competitive with performance processing experts on x86 architecture. So there are quite a few benchmarks on YouTube, again from this guy called Alex Ranking, which is working on Halide full time, and it's really it's really interesting to see that this Adams autoscheduler does produce an optimum version already, or near optimum version, with anything that an expert would come up with. Unfortunately, ARM is not yet target here, but this is something which you can already see is worked upon. And this is mainly due to the fact that the original paper, so Adams 2019 is also a paper, due to the fact that the training data didn't include any ARM test data. So that's why ARM is not yet targeted, but is something which is probably happening in the upcoming future.
So
all right.
Maybe can I create a presentation, and also the visualization is quite helpful. So I had in the back of my head some optimization that is done directly on the algorithm, like auto-vectorization. And that's why I was wondering how you could separate the algorithm from the scheduling and way of order of getting the data from memory. And so if I understand you correctly, some direct optimization which looks at the algorithm, like auto-vectorization, is not performed, but actually the search space, all possible orders are considered. or maybe then some deep learning is used to prune this huge search space.
Yeah. So you mentioned auto-vectorization. So your compiler is actually doing or can do some of it. So if you happen to have a for loop and you iterate over your, I don't know, float array, say, and you happen to compile it with -03, then your compiler may or may not does do some auto-vectorization. But in my experience, and probably in the experience of the Halide authors, this is very brittle and prone to not working anymore if you happen to change one little piece, because what the compiler is doing is basically pattern matching. So it creates your AST, right, and then it does pattern matching. And if we see some optimization potential for auto-vectorization, then it's doing it. But you cannot rely on this feature. And so with Halide is as you formulate your algorithm in a Halide function, and then you have your scheduling, the capabilities from a compiler implementation in this regard is much more powerful, right? Because you can see you can exactly see the data flow or the flow of data and the sizes you're dealing with, and this gives you much more power on the backend side to do all of this stuff which previously had to be done by hand. And yeah, so and your question, if I understood correctly, with regard to the auto scheduling, is that of course you could do like try out different cache sizes, tile sizes, loop unrolling, caching, or just reloading data, or pre-computing stuff, and all this usual stuff you would possibly try out if you wanted to optimize your given piece of code or algorithm. This can be done automatically just by expanding this tree of possibilities and doing it automatically. And in fact, if you happen to switch on the Adams autoscheduler during compile time, it actually tries different approaches and measures the number of assembly generated and also the runtime, and then just decides during compile time what is the best approach here. So it's quite fancy in my mind.
Cool.
All right. So yes, this is the last slide I'm having for you today. Again, if you want to know more about Halide, they do have. I mean, you can see that it's like a university project a bit. So the documentation is a bit lacking, but there are some tutorials on halide-lang.org, which are quite helpful, and also just trying things out. If you happen to have this problem, I would definitely look into Halide, because there's a lot of potential there, and also there's a lot going on already. So a lot of companies starting to look into Halide as a solution for especially for embedded stuff, starting to look into Halide as a potential solution for their performance issues they are having. All right.
Thanks a lot.
Yeah.
This was really interesting. So maybe this slide is the right time to ask a question I still have in the back of my mind. So I see 3 different areas where you've been talking about now. This is on the one hand audio processing, on the other hand machine learning, and then Halide, which probably connects those two by being the suitable processing library. But from the application, from the practical side, did you do any projects which cover both and you are allowed to talk about?
Probably not. So what I can say is that I'm using Halide in commercial projects right now. So this I can say. So I'm using it actively in projects, and this is so this gets used in commercial software already. Also, I didn't mention it because I thought it was a bit too much of information, but there are several ways to include Halide into your commercial project. So you can, I mean, the stuff I was showing to you was JIT compiled, so you could change it before running your during runtime, say, or as a command line parameter. But it also can be, there's like a thing which is AOT, so ahead of time compilation, where you can statically link your optimized algorithm into static library and ship it with your application. I think Halide is MIT licensed, so it's just perfectly fine to use it in any commercial projects. And so yeah, what I can say is that, I mean, obviously it fits, and if you also look at the examples and the tutorials, it fits very much into 2D image processing, because this is usually something which is computational heavy, and just is in need of all those different optimization techniques I was talking during my talk. So this definitely hits a nail here. All right, so just looking at the YouTube chat, or the Jitsi chat, so there's not any more questions. If you happen to have like consultancy needs or need training or workshop, feel free to just to contact me over at kai-wolf.me. Also, happen to hang around in the different user groups. So I was previously quite active in the Munich C user group. Now also will join the Karlsruhe user group in the future for any further questions.